Hello, everyone. Um, Welcome to another Haskell study group. I'm your host, Ram Vedam, with the Functional Programming. Today, we'll be discussing and diving further into the basic data types that are provided in Haskell and actually get into more of the idea of types and their role in designing and writing and reading Haskell code, and just some basic definitions that you need to be aware of when especially reading Haskell and related literature, as well as when you're communicating with others regarding Haskell programs, because a couple of these concepts are necessary in order for you to understand the way certain ideas kind of proliferate, especially when it comes to designing larger scale Haskell programs. Last time, just to give a brief review, we covered a lot of the basics of the basic data types, the integers, strings, how to construct a basic type ourselves. We've introduced the idea of a type constructor. I will go into more detail today a little bit about what type constructors are with respect to the levels available inside Haskell and namings and things like this. Um, we've also introduced the family of different numeric types. Other than just integer, like I mentioned, we talked about the fixed precision integer word, as well as the fractional numerical types such as rational, scientific, float, fixed fixed nums, as well as single precision, double precision, floating point. Today, we're going to start our discussion with just an understanding of Booleans a little bit more, just one more time, just to give a review, because last time has mentioned we have Boolean expressions that actually um, can take not only Boolean types, type constructions, using either true or sorry, we can't just explicitly call true, either using expressions directly or passing in a construction into an expression and have it evaluate. What is this? Imported. May have to restart. Okay, got it. Let me just do one thing here. That's what's messing it up. Okay. And we know, or false, these are your basic, type constructions that are part of, if we go and look at bool, it is the data definition, data declaration, which we introduced last time. As you can see in this thing here, we have our data declaration with the type that we specified here, as well as the two type constructors, false and true, accordingly. And these can be created on the fly through an expression. So like in the case of not x equals 5, you will see that, let me actually first give an x equals 5, and then say not x equals 5. What will first happen is we'll first evaluate x equals 5, realize that is true, and then that true is actually constructing an instance of a true type, and that's passed into not, that's then subsequently evaluated and returned false. Last time we also covered some basics of the infix operators as well for Boolean expressions, and these are expressions that can not only take the type variables, the type constructions themselves directly to create instances of the types like this. For example, we could pass in true and true directly to the logical AND operator here, and it will go ahead and evaluate it accordingly. But we can also provide expressions which can construct instances of these types. And those as well will construct the appropriate Boolean type constructions to pass into the overall infix expression of logical AND, and then that gets evaluated into a new type being created at the end. The importance of this is this is kind of illustrating some of the notions of the data types themselves, just the notion of what is an actual type itself compared to what a type set is. And this is related to what we talked about when we talked about data declarations and how data types are actually defined in Haskell. The one thing to be careful of is data constructors are values that show up at the data constructors themselves are different than the type constructors, okay? So the type constructors are, remember, the left-hand side of the data declaration, okay? So this myBool here in this data myBool is declaring that there's a set of one or more type data constructors that will that automatically should infer to be a member of this top level type. Now, this kind of is related to the way Haskell works in terms of where the individual names and variables reside in the underlying Haskell compiler, and how the Haskell compiler itself uses this information to infer further pieces of information from your code in order to ensure correctness, that the types all match up, for example, that you're creating instances of the appropriate type, in the case of type classes, that they are enforcing and creating instances of a type class because that specific subtype implements all the associated operations and so forth. I'll touch base a little bit more about type classes in a minute. But the main reason I'm bringing it up with respect to Booleans is because this is a much more simpler type that's actually available in the prelude, but since its data declaration is pretty simple, it can be we can talk specifically about what is the difference between the notion of what's considered to be the type level and what is considered to be the term level of a piece of code. Okay. So what do I mean by this? Well, to begin with, I think it's important to know the different types of entities that are available in Haskell. Okay. Entities are these definitional objects that you'll be probably playing around with day to day on your Haskell code. Okay. And there are documented 7 different types of entities. Okay. Functions, we all know. Variables is another one. Term level variables is another one. So we need to talk about what term level is in a second. Then obviously we have type level variables or type variables. We have data constructors. Okay. Constructors. We have type constructors themselves. And then we have, on top of type constructors, we have type classes. And then finally, we have, at the highest level, modules. Okay. These are all related to how you would organize code and how names are actually accessed at the appropriate level. Okay. So to begin with, I think functions are pretty self-explanatory. They are just simply whatever set of Lambda expressions that you've created based on one or more variables that are or uh, free variables that are associated with the Lambda expression, which is free because it's not bound at the time that the expression was defined, and it will not be evaluated and so forth. At the same time, we have then term level variables. The phrase term level actually means something very specific in Haskell, okay? And I think it's important to actually be aware of what that is. So there's two levels of what's it? How can I explain this? So when your code is being executed, okay, when your program is being executed, the values that are created, the level those values, those concrete values live in, those are the values that are living in what's called the term level. Okay, these are the terminal level. This is at a point where essentially those values are bound to some instance of a variable. They will not be changed. And they are ultimately what is used in the code when your program is executing. Okay. Now, this is different than type level variables because at the type level, what's happening is you are constructing it for the purposes of analyzing the program. The program hasn't actually been compiled. The program hasn't actually been executed. It is being used for static analysis, okay? It is mainly being used to verify that essentially your types line up, okay? And at the type level, what resides in there and is used at this level are your type variables, your type constructors. So, for example, the my bool that we defined earlier, this or even bool, or int or integer. These are type constructors that are going to be used mainly in the case of especially defining functions to ensure that those functions are constrained, and in the case of verifying for evaluation, the types all line up and so forth. So we have type variables. Type variables are generic, all right? So those tend to be lowercase variables. We've seen this already in the case of, say, looking at the signature of a very simple expression that we wrote, the add expression. Let me just go ahead and pull that up. It's like, for example, if we had a simple add xy equals x plus y here, okay? Example of a function, a generic add. Actually, I can actually even show this to you using operator add, info plus. Okay, so this lowercase a here, okay, hold on 1 second. This lowercase a in the type signature of the operator plus, that's representing a type variable. You don't know what exactly the type is, okay? It can be any type, okay, that's being passed in. And it's going to take two types, two instances of the same type in this case, since they both have to be the same type, and it'll return an instance of the same type. Okay, this is what a type variable is. Above this, and we'll dive into this a little bit if time permits today, but is type classes, okay? And a type class, all you need to know right now about type classes are they are literally a set of operations, okay, that are defined with respect to some polymorphic type, okay? And we'll talk about polymorphism today in more details, but given a polymorphic type, the set of operations that is defined with respect to that polymorphic type can represent what's called a type class, okay? If a type has such an instance, if it has an instance of such a type class, that means that values of that type can be used in particular operations that are defined for that type class, okay? An example of this type class we've already seen, EQ is a standard one. EQ is a very simple type class that you can look at. It deals with equality. Again, I'm merely mentioning it because it's part of this hierarchy of types of entities that are available in Haskell right now, and we'll dive into it in more details in a little bit. After type classes at the type level, we are out of the type level, and we're now at the level of organization, okay? And what I mean by organization literally is a code organization. We're trying to group specific pieces of code across different files, maybe, and so forth. For that kind of grouping, we have modules, and modules is a construct that's been around for quite a while. You guys are aware of modules from your programming language of choice. The idea is very, very similar here, but it is a different level in terms of naming entities in Haskell. Okay, and based on which level that you have, you will have a specific access to the names and the variables that are associated with it. Okay. Boolean, in its case, to go back to what I was talking about with Boolean, Boolean being available in the standard prelude, there are other things that are associated with the term level and the type level things for Boolean, but in terms of the operators, the majority of them are available in the prelude. Most of the standard logical operators are available in the standard prelude, but if you need more operations, I think data.bool we can actually import. There's more operations available in data.bool, and you can look at what's available in there. It's not just logical and logical or. There's otherwise and not. These are some of the basic operations that are available in there. And there's a couple of things related to the type classes that are available too. That's in the standard prelude. That some of which may not be in the standard prelude as well. But I'm pretty sure most of data.bool is in the standard prelude because it's used in a lot of other functions too for obvious reasons because it's used to implement conditional logic. So that's Booleans. We've talked about conditionals as well. Okay, so let's talk about tuples. So today our next topic is going to be obviously on tuples. And what are tuples? Tuples is a special kind of type, actually. It is a type that allows you to store multiple values and pass around multiple values within a single composite. It's one way of creating composite values outside of creating a structure or a record type or a class. I'm forgetting there's ways to create composite types that we're going to see soon enough with algebraic data types and creating an abstract data type for an object, much like classes and objects in other languages. But a tuple, as many of you know from coming from other languages, is simply a way to create a simple composite value. The syntax associated with tuples is very distinctive. And it is used both at the term and the type levels, going back to what we were talking about earlier. And the number of members of this tuple is actually fixed at the time that the type is constructed. Okay, you've seen this in when you may not be explicit when you've created this, but you've seen this when you've used tuples in other languages, say like two tuples or pairs or triples or quadruples and so forth. The number of actual members for a pair is fixed at 2. The number of members to construct an instance of a triple is 3, and it is fixed, and so forth. That number, known as the tuple's arity, determines an instance of that tuple's type. Okay, and this is a very important point. Each type of tuple has its own. It's created has its own type. Even different tuples with different arguments, they may be members of the same tuple, but they may be different types themselves. An example of this is when we're talking about pairs. All right, a pair with a number and a string is going to be completely different than a pair with two numerics. Okay, this is very, very important to remember. Although they are part of the higher level type, if you will, they're members of the type pair. They are not necessarily the same type themselves. Okay, they're disjoint in terms of their actual implementations. Pairs, triples, and quadruples are all instances of type tuple, but they themselves, I've kind of considered them to be distinctive type families, and I think it's important to know that although they are all technically tuples, they themselves have different characteristics, and I think that's pretty obvious based on the fixed number of variables. Okay. And yes, as I mentioned, number of tuples is known as number of members in a tuple is known as the tuple's arity. Yes. Just like any other operator that we saw, operator plus, minus, and so forth, the actual construction of a tuple can be done using either prefix or infix notation. Okay. So let's cover some examples of this, okay? A couple things to note for those of you following along in who is using our reference the recommended reference. There is something that has changed with the construction of types. So I'm going to illustrate something that has changed in terms of DHCI versus what's available in the Haskell book itself. This is something that I encountered the other day, so I'm just bringing it up for folks who are following along using that supplementary reference. But to begin with, in the most simplest things, let's actually go look at the operator that we're going to be dealing with, okay? This is the comma operator, okay, used to create a constructor, an instance of a tuple, regardless of whether it be a triple, quadruple, and so forth. ignore all the type classes that it implements. Immediately when you see this, okay, you should see that this differs from what we've seen before. One is that it requires two different type variables, okay, A and B. Before, we've always been dealing with examples that contain a single type, and it's actually been enforced that they should all be instances of the same type. This is an example of being able to essentially take two different types and create an instance of a new type, okay? However, this is not restrictive to saying that B cannot equal B to A, meaning that A and B doesn't necessarily have to be different types. It's just that the operator itself supports creating instances of tuples that contain different types for each member, okay? This is a very subtle but important point, okay? When you're reading these type signatures, okay, the generic type variable that you see, even if it's different, it may not be a restrictive difference, meaning that it is not enforced that the types have to be distinct. It is just that the operator itself is generic enough that you can go ahead and at the term level bind them to values of different types itself. Okay. The return value of the construction of this is what's known as a product type. Okay, a product type you could think of is a logical. It's a logical AND. All right, we've kind of brought this up when we were talking about sum types earlier with the data declarations of sum types. But a product type itself, being a logical conjunction, basically means that you must supply both arguments in order to construct a new value. Okay, this is a very important thing. Like otherwise, you'll get a partially evaluated function, and this is related to something that I've seen with being a slight difference versus what's in some supplementary material, particularly the reference that we've been using to actually go through the Haskell language and what newer versions of the Haskell compiler allows us to do. At least on the REPL, okay? And we can create, as I mentioned, these pairs using this very simple prefix notation, or we can use infix notation as well. The way we would do that is we could also do x equals 8, 10, or 8, 1 in this case. And if we could look at the type of x, you'll see that it is a tuple of two different types that takes in two different numerics, and it returned a numeric itself. But we can also use different types. So like 8 and hello, you'll see that this creates a new type here. If we do a type, let's do an x equals 8 hello, and we actually go and look at the type itself, we can see that this takes in a numeric and it actually returns a list of a numeric and a list of characters. Because the characters here in this case are themselves going to be any sort of string. And since it's a constant string, it's going to go ahead and can return a constant string itself. Recall that string itself is nothing but a type alias, which is a different name that we can associate with a subtype and a different implementation just for brevity's sake, or to improve code readability, which is actually encouraged to actually create some type aliases when needed. So this is where the slight difference is. Now, some folks coming from older versions of Haskell, if you have different older versions of Haskell, I encourage you to try and upgrade to, like, say, the latest version, like 8.10.4 at least. You might end up getting like an error when you try to partially apply the comma operator, the tuple operator, because in earlier versions it was the case that since there wasn't any way to actually show the partially applied function, um, it was the comma operator itself, the tuple operator, kind of expected that you should have a minimum number of arguments. But that's no longer the case. You'll see actually when you return it, you'll end up getting a partially applied function. We can actually go ahead and assign this to create something like, say, pairs with 9, to create all pairs that are associated with 9. And if you pass in another value to it, you'll get up an appropriate tuple of the different types. Okay, and again, this is a generic partially applied function, meaning that the second argument could be any type. So we can not only just pass in 1 like we did before, a numeric type, we could also pass in any other type too as well, and it will work just as fine. This is important to note just because of the fact that this means that you can now create partial tuple constructors, okay, tuple factories for different types of constant values associated with it. One thing to be aware of, and that is just really from a best practices standpoint. I mentioned tuples, triples, quadruples. Best practices dictate if you have if you have a tuple that's more than 5 arguments, all right, and that's a quintuple, I think it's called. It's normally encouraged that you go ahead and move that into a more composite data type that we will see in later discussions. But 5 or less for everyone's, I think you'll be okay with actually, or at least you could get away with actually being able to use tuples directly and being able to take advantage of some of the things that are available in terms of the API. So given a tuple, we have a couple of functions that might be useful. So let's go ahead and create our simple example here. And again, I will visit the type signatures on how to declare functions to take in a tuple and so forth later on in today's discussion. But for the time being, just bear with the step-by-step kind of like approach that I'm taking here. But let's go ahead and create an example of let's say this pair with let's just create a concrete pair for the time being, all right? So we'll go ahead and say that this is basic pair. I'm going to just use basic pair as an example, and we'll say that this is 9-1. This is going to go ahead and say no type signature. Let's go ahead and add the type signature, basic pair, integer, okay. Okay, so now in Haskell, you actually have a couple of very nice, just like other languages, APIs for accessing the first and second argument, at least when it comes to pairs, okay? And that is first, okay? And if we look at the signature of first, it takes a pair and returns the first argument. All right, that's obvious from the signature. Second is not spelled second completely; it's spelled SND. This guy obviously is going to take in a pair and return the second argument itself. So for people who are looking at this and saying why FST and SND, why not first and second? I'm not entirely sure what the reasoning was to use as few letters as possible for first and second. I mean, first it makes sense. Second, SND looks a lot like sending something, so it took me a little bit to get used to it, but obviously, this you'll once you get used to it, it's not a big deal. So we could see that if we pass in our pair that we created first, basic pair, we get the first element. If we do second, we get the second element, and so forth. There are other things that you can then use to, for example, to manipulate tuples. So like in this example here, we've defined here the example that this is going to be an integer, and then it creates something concrete here. But if you're in the REPL, you can also do something, and I'm mentioning it that it's only in the REPL just merely because of the fact that I don't know if anybody would use this technique in real code, in code in a file, right? But you can, in the REPL, also define tuples where you can restrict the type that's actually being constructed at the time of constructing the tuple. And I'll give an example of this. For example, let's say that we are doing something like this, okay? We have my tuple 1 blah. If you look at the type of my tuple, 1 is actually determined to be a numeric, all right? Strictly a numeric, which means it could be anything. It could be fixed num, it could be int, it could be integer, it could be word, it could be so forth, all right? Its representation is not at all constrained in the type information, okay? What you could do instead is you could actually go in and say, hey, I want this variable to be strictly an integer, okay? Now when we look at the actual tuple, you could see that the proper construction is created. So it's not actually an expression that takes in a type class anymore. It's now an actual physical type, concrete type instance, because we constrained it. This is something that's important to be aware of that you can do inside tuples, but also in other places too. It's very useful. This colon, if you remember, is defined as, it's kind of used to essentially specify what the type signature is going to be associated with a particular instance of a value or a variable if you're defining type signatures inside your file, as we did with like basic pair. One more thing to be aware of in terms of tuples, especially pairs, is sometimes you may want to swap the values in a pair. So there is a swap function for tuples and for pairs, but it is not actually located in the prelude. In fact, if you type in swap, you'll end up getting this error. Swap is not actually a variable, it's not in scope. Okay? If you try to, and it's the same thing with, if you try to do info swap, okay, as well. So what you have to do is you have to first import data.tuple, okay? Data.tuple contains swap, obviously. Now if you do an info on swap, you will see that swap takes in a pair and then returns a new pair that has the argument swapped. And we could see that if we do myTup here, we'll return blah and 1. And then, obviously the type signature has now changed because now it's no longer an integer with a list of characters. Instead, it's now a list of characters with an integer. Two different types, they're not obviously equal to each other. One of the nice things is you can also use, one of the nice things with tuples is you can actually use, especially if you're dealing with like numerics, you can actually use them in higher level expressions. So for example, if you're trying to add in the first of, say, 0, 5, okay, you can see that we can actually, without parentheses especially, it will know how to do right to left associativity, and it will actually go and construct the appropriate instance here. In this case, it's grabbing the first value of the pair, which is 0, and it's adding it to 2, which gives us 2. Okay, we can see the same thing happen. Can I actually do? Yeah, sweet. Okay. With second 2 as well, the same issue, same kind of nice things. The pair syntax, especially the itself, is used is a very special syntax because it allows you to, at least Haskell allows you to use it with respect to pairs, especially. I don't know necessarily about triples and so forth, but definitely with pairs. You know what? I take that back. With any number of arity tuples, the comma syntax is very special because the signature, the type signature that you use for function declarations and for variable declarations like this, is the same syntax that you would use to actually construct an instance of the type. So if you look at this example right here, we are using this syntax to determine what types are we constraining each member to be, okay? And we're creating concrete values of these types when we're actually constructing it, okay? This is very important because of the fact that this basis is used for things like pattern matching, because when you write functions that take in a pair and so forth, the actual type passed in is going to look exactly like the argument being passed into the function when you're constructing it. Okay. Obviously, there's many. Let's say that we want to create, for example, an example of this of a function that can take this. Let's say that we want to add pairs, right? And we're doing add pairs element wise, all right? So what do I mean by add pairs element wise? What I mean by that is if we have a pair a x and y and a pair z and w, okay, what we'll end up adding to is, what we'll end up returning is x plus z and y plus w, okay. So we could define this as a function that takes in an integer okay, and what this does is it returns a function that takes another integer, and what we'll return is an integer. Okay, keep this in mind because we're going to be digging into this in a little bit about the type signature, but this is just an example of how to use this in defining a function call. Okay, so now we can use add pairs. Now this is obviously I don't necessarily need to define the function name this way. I could just simply say add pairs, but because I have a comment there, actually I may just do that just to make it a little easier. So let's do this. Now I'll touch base on this, but this is generally best practice that I'm doing here, I'm indicating here. So I'm just going to explain this very briefly. You might notice that I'm not using x, y, z, and w inside my function signature here. It is typically best practice that when you're using type variables, okay, since I'm using these generic types, although we've constrained the types in the type signature, these are just generic variables themselves. You want to start with A and work your way down, but I'm just mentioning that this could be x, y, and z and w, but this is not. It's not necessarily going to be used. I'm just using this so that we can make this potentially generic later on. So once we've done this, we'll get a plus b, a plus c, and b plus d. Okay, so now let's compile this. Everything now is compiling. Now if we go ahead and look at our pairs, you'll see that we get the appropriate type signature, where is it defined, and so forth. If we add our signatures, you'll see 4 and 6. Okay. Are there questions? Okay. So we talked about tuples, but obviously tuples are dealing with composite values of different types. Technically speaking, they could be heterogeneous composite collections. How can we actually define a collection with multiple values within a single value? So essentially, how can we go and define a list? Well, list is available. I mean, it's a very core data structure. They are different from tuples themselves in three very important different ways, but very important ways. One is the fact that all elements in a list must be of the same type. Now, this is definitely different from folks coming in from, say, a language such as Common Lisp, where you have essentially the ability to create heterogeneous lists and heterogeneous sequences and so forth, which becomes the basis of much more complex data structures available in that language. But in Haskell, lists are treated, all elements in a list are treated to be all of the same type, and if they are not of the same type, obviously you're going to get some problems, and I'll show you an example of this in a minute. Additionally, it has its own distinct syntax. Okay, so we saw before with the tuple, it uses x and y within a comma in parentheses versus is a tuple. And with lists in Haskell, we have bracket syntax. We have x comma y represents some list of some characters. Okay, list of any type. Okay, oops, not any time, any type. Sorry. All right. The third difference between these two is lists are dynamic, okay, in terms of arity, okay. What I mean by that is the number of members in a list are not specified at the time the list was constructed, okay. With a tuple, the arity, the number of members that are part of that tuple instance is immutable. It is fixed at the time in the type signature at the type level, okay? And we could see this with respect to our add pair example here, okay? Or even our basic pair that we see right here, okay? You can see, obviously, that this basic pair or even this add pair requires at least 2 arguments before it can actually go in and continue the actual evaluation. Okay. With lists, if you don't know, you may never know how many things are members of a list. Okay. We can touch base on this a little bit more, but let's go through an example of this, okay? We've seen already our tuples. Let's go ahead and create an example of of a list, okay, of a list of strings, okay, or a list of strings. So let's do this. Let's create, let's do Paya. Okay, we're gonna make a list of fruit, for example. So fruit list. Okay, you might have example of with a variable that we're getting bind that will get obviously injected into the list. I'm using the concrete syntax to construct. This is just a convenient syntax to not calling list explicitly. It has a review there. This might be banana here, apple, orange, so forth. Okay. So we have our fruit list. If we, obviously print this guy out, it'll pretty print it to the appropriate list values. But if we look at the actual type signature of fruit list, we'll see that it is a list of strings. Okay. Again, reminder: when you read the list of characters, think string, because string is a type alias to a list of characters. Okay. But what this allows us to do is we can actually leverage a lot of things available to both. So a lot of functions and operations that are valid for lists of any value. This includes things like what we saw before, like concatenation. So if we had another list, like a vegetable list, okay, let's say tomatoes, potatoes, some celery, and so forth. We can actually combine these lists in, say, produce is just nothing more than our fruit list plus our vegetable list, and you'll see that our produce has now been flattened and has all of those values associated with them. Okay. You can also do concat that we saw before. So if we had, for example, produce created as a list instead, fruit list, vegetable list. Okay, we can use, if you remember what our concat operator does, is it takes a foldable and creates a list. Okay, we can actually go and concat produce, and then we get essentially the same concatenation. Okay. And this is the same idea that we saw earlier. All operations that work on lists of any type work automatically on lists of strings. There are many standard functions available with the list data type, and we will encounter more on lists later on. But I thought I'd at least introduce this to you right now based on some other prerequisite notions that I've been reading in some of the supplementary material to kind of illustrate that the difference between tuples and lists, and especially, and this will confuse some early beginner folks who aren't familiar with the syntax difference between the bracket syntax to represent lists of the same type, especially versus tuples, which tend to potentially be lists, composite values that contain potentially the same type, but most often maybe of different types. Okay. Let's see. One more thing that I'm missing. Okay. One thing that I'd like to point out, actually, I'll bring that up in just a minute. Let's continue. So now we covered a lot of the basic built-in data types, such as bools, tuples. We technically introduced ourselves to the numeric types and especially because we talked about the numeric types, we had to introduce the numeric type class as well as the EQ type class. And again, info on the numeric type class is the instances that are already available for you, what operations are associated with the numeric type class, and we talked about EQ, which again, if we look at EQ's information, you'll see that there are a lot of instances of what EQ is around, but more importantly, EQ tells you that you need an instance of EQ has to define equals and not equals as well for these type classes. Okay, but although we've introduced types, built-in data types, some basic ways of creating composites, some basic things about type classes, we never actually delved into a lot of these concepts up until now. And we'll touch base on some of them in this particular part of the discussion. But in a lot of cases, we'll be encountering them more and more as we cover some of the more higher level constructs that are available in Haskell, especially when we encounter them in designing some real world examples. Okay, so let's revisit the data type declaration that we had earlier. Okay, we had this example with the Boolean that we saw. I may end up coming up with a separate example, but we'll use this for now. Okay. As we've seen, that this declaration consists of, and as was mentioned throughout this discussion, this consists of a type constructor and one or more data constructors, as illustrated by false or true, each of which being a zero argument type constructor. Data constructor. Data constructors, as you probably figured out, are the values of this type construction. Okay, these are the values of a particular type. We're saying my bool has values false or true. Okay, but false or true themselves can be one or more different instances. Okay, this is very important to note. The values themselves are bound at runtime, and they are accordingly going to be one or more values, although ultimately they'll get reduced to either false or true in this example. In a sense, though, they're not just values of a particular type. Data constructors are also, because I'm talking about instances, they're factories. Okay, they're functions that allow us to create data of a particular type. The full understanding of this you'll see when you come up with more and more examples in Haskell. But the idea is very much like when an expression is evaluated to a value, at that time that appropriate type is going to be constructed, and that appropriate type construction is then checked through analysis to static analysis and verification to be of one particular type or one or more several type families. It might be even associated, depending upon the signature of the function that you're evaluating. It might be associated with and it might be verified to be a member of some sort of type class and so forth. So there's a lot of these nuances in how the Haskell type system to determine some of this. But the bottom line is the data constructor ultimately constructs a new instance of itself from a value that's being returned by a particular expression. And a lot of this interaction is used later on by the Haskell compiler to ensure that your code is correct. Okay, that's a very important thing to be aware of, and in a lot of cases, it's the very foundation of how Haskell kind of works. Okay, so in Haskell, in a sense, nothing is essentially untyped. Okay, and there's a reason for this, and it goes back to what Haskell was designed after. Okay. Haskell itself has some claim, and it's I can't find any sort of like literature that strictly spells this out, but it is considered an implementation of the pure lambda calculus, but more specifically, the pure typed lambda calculus. Okay, a typed lambda calculus, obviously, as the name points out, is a lambda calculus with lambda expressions where things are typed. You have some sort of primitive or some sort of type system associated with that information. Okay. This goes back to a research system that was created back in the 70s called System F. But Haskell improved on this research system in several ways, several features, and we'll talk about some of the features available. Just to give a hint, there is type inferencing in Haskell. System F did not have it. There's an understanding of they genericized recursion. They allowed general recursive functions to be available. Mainly, especially if you use Haskell a lot, you'll see this, especially in their implementation of pattern matching, how you would actually normally define recursive functions inside Haskell using particular patterns, and it's also can be used. How they implemented recursion can also be seen in other instances based on how you define like inner functions inside lets and wheres and so forth. But the question still stands, all right? Like up until now, we talked about all these different types. We've talked about all these different basic things, type classes and so forth, but we never actually answered the questions, why do we need types in the first place, all right? And I think that's a very important thing to discuss. Okay, what is their role in a larger scale system? Okay, type systems themselves, the idea can trace itself back to logic and mathematics, where we define a logical framework of something that imposes constraints to the problem, to the universe, in such a way that we can enforce correctness guarantees to occur within this universe. Okay, types themselves essentially are designed to impose those constraints. Okay, so when you're looking at the large-scale universe of possibilities of any sort of system, the constraints upon which you can work within that system are your types in a lot of cases. So a well-designed type system is specifically used to eliminate the sort of logical errors or fallacies that could occur through the course of actually running a particular system, because it violates some sort of type constraint that you've imposed and you've designed around to ensure that it stays within that universe. Okay. For example, this is a very typical thing. In Haskell, unlike in C, a Boolean value in an expression, whether it be in an if expression or in some sort of higher level Boolean expression, must be a Boolean value in order for the expression to evaluate itself. Okay. In some languages, for example, C, you might end up having the rule that 0 is false and any non-zero value means it's true, which means you could pass in anything into there. But then you have this problem that you've essentially introduced, which is a class of errors where potentially something is being used expecting that the value should exist at the time at runtime, only for you to realize that the person who wrote the code forgot to initialize the value, which means there's garbage in that area. It wasn't cleared. and the logic itself doesn't assume that it doesn't check that at all, because you can't. It's using the zero or non-zero-ness of the value of the variable in order to determine which branch to go into. It ends up, violating that, and it allows certain branches to be executable when they shouldn't be in the first place. Okay, this is just a simple comparison between the two, but it illustrates the same point. This is one of the reasons why a type system, a much more stringent type system, is necessary. Okay, it is true that C has a type system, but C's type system is much more weakly typed compared to Haskell's, which is why it's often the case that you'd want to compare the two to see what the differences are. Okay. Additionally, Haskell incorporates what is called static typing. Okay, this is obviously not new to any of us who've written in compiled languages, whether it be Rust, C, Go, Haskell, Ada. There's so many, I'm not going to name them all, but or even us common lispers who've used type annotations to further restrict the compilation generation of particular assembly code, because with type hints you have the ability to actually further provide hints to the compiler to actually optimize your code for efficiency's sake. So what does static typing mean? Static typing essentially means that when you're generating your machine code, okay, that is when you're compiling your code to machine code, it does its type checking to verify that your code types all line up, which means code that's being executed ultimately will work as it is intended, because we've enforced that type check ahead of time. It's not going to suddenly violate those type checks, those constraints, and to create unpredictable behavior, which is often the case when you're in languages such as Python and you're not too careful. I'm not saying that you can't have type-safe code in Python, but the challenges of creating type-safe code in Python is much more, because we don't often document those types in Python or Ruby, or in a lot of dynamic languages that are being in use today. However, some of that's being mitigated with current introductions to, say, like, gradual type systems that are being introduced, such as Flow, or in Python 3 they have now the optional type checking and so forth. But these have to also interact with existing systems, so you might end up having still the dynamic check that is often the characteristic of those types of systems. Whereas in Haskell, because this is done in compile time, it is reducing some of the more obvious tests that you may have to write out of necessity in Python and Ruby, just to make sure that the type violations don't actually occur, right? Again, this is the nature of the runtime system and the ability to be able to have a dynamic language. But the fact of the matter is you have to go ahead and write those systems to get more robust code. Whereas with types being available in with a static type system like in Haskell, you can avoid some of those potentially. Now, I'm not saying it. Now, those of you who might be thinking that type systems are like, the bee's knees and it's going to, solve all your problems, I must warn you that, type system also puts you into a false sense of security if you're not, obviously checking to make sure that your, requirements are being, appropriately modeled correctly in the types that are being used to enforce system correctness. So be careful there. One of the advantages of a very good type system, all right, so static verification is one reason why we need types. Another advantage is obviously hints to the compiler for compiler optimizations. Okay, a very good type system can enable the compiler to actually do some otherwise potentially behavior-changing things while maintaining type correctness. Okay, it can allow certain optimizations that it can do behind the scenes at the assembly level, as long as it preserves the types and the correctness in the program has enforced by those types, you're actually okay to execute those optimizations, which means you might end up getting, uh, faster code, much more efficient code. That's a very decent advantage to actually keep track of this. All right. The cost of this type system, okay, of such a strongly typed type system, oftentimes is upfront investment. When you are designing your system, you must design around the types in which that you must design your types much more stringently and more proactively up front instead of later on. They're not discovered through the process of actually writing code. Okay, this is slightly different than, say, if you're using a dynamic language, which oftentimes allows you to do, or even a language like Lisp, where you're often exploring the space and trying to figure out what your types may end up being later on, encompassing them with particular rules, defining those types, and then using those types later on as hints to the compiler to actually improve code efficiency, not necessarily verifying code correctness, because you've already incorporated the correctness checks in tests, and whether it be integration tests or unit tests and so forth. Since there's this upfront investment, I hate to say it, you're going to spend quite a bit of time talking or convincing the Haskell system to verify your pieces of code. It might actually be a little bit frustrating at first, because if you say some things are certain types and Haskell determines a type violation in some cases, it will tell you that, and you will spend quite a bit of time correcting compiler errors. Now, that said, once it starts compiling, if you think that it will just run the code, you're right. It will run the code, execute the code. Whether or not it implements the system requirements or application requirements is a completely different story, because it's dependent upon whether or not you implemented the requirements and design the types accordingly to enforce those requirements correctly. So, while it is true that it will work as designed, that phrase must be taken very, very literally, meaning that if you designed it incorrectly, it will work, but you designed it incorrectly. So, type design itself is a challenge. Haskell makes it so that if you designed your types right, if you actually implemented those requirements correctly, it will go ahead and do your bidding. It will make sure that the rules that you've enforced through those type constraints are actually being adhered to, so that the system works and behaves the way you expect it to, based on those type decisions that you've put in ahead of time. Okay. Let's talk about type signatures in a little bit more. All right. Let's take, for example, our character. All right. When we're actually querying types, okay, remember we have this type command, which I'm using shorthand :T for. Okay. There is, as I think I mentioned before, a way to actually get the REPL to always allow you to return the type, and that is by setting +T ahead of time. Okay, this allows you to get the type every time. What it does is it assigns the type to a variable called it. You could think of it like iterator. And it will determine the type from that variable that it implicitly defined. And since this is a REPL, it's often the case that you can go and IT will always change. So if you pass in hello or 5, sorry, it'll always go ahead and redefine it and do the thing accordingly. When we particularly, one thing to note about the differences between what's being returned here, and this is why I went ahead and set the plus t so I don't have to specify the querying every time. You might notice that when we're always providing different types of numeric types, let's try whether it be a double or a fractional number or a integer or so forth, you'll end up getting a type class rather than a actual type associated with it. Okay. The reason for this is at this point in time, the compiler doesn't know which specific type this type is associated with. Okay, it only knows that it is a member of this higher level type class. Like for example, 5. Okay, this simple example. 5 is a whole number, but 5 can be represented as either a fixed precision integer. It could be also implemented as a integer itself. It could also be implemented as a word, technically speaking. Also, it could also have been implemented as a single precision or double precision integer as well, or a fixed integer. There is no way of knowing by just saying 5 as to what its underlying representation is. So the best thing to know is since all of these types are members of they're all instances, or they all implement instances of the numeric type class, it's the underlying compiler infers that, okay, this is some sort of numeric type. I'm going to go ahead and construct this numeric type and then go ahead and implement this, okay? And this brings us to what, something about a particular feature about Haskell's type system and about Haskell in general, okay? And that is Haskell's type system is what's called a parametric polymorphic. Well, Haskell's type system implements polymorphism specifically using parametric polymorphism, and it could also be constrained, right? It's parametric in the sense that the fact of the type variables that are being passed in the type signature can be of any type, and those associated rules can be constrained or relaxed based on whether or not you're creating a more generic function or not. An example of this is if we look at ID, okay? ID is your standard identity function that takes in a type variable and returns a type, that takes in some sort of type input and then returns another type output. It returns the same thing, as you can see here. An example of this is we return 5. You can see that what it did is it constrained the type to being a numeric type, and then it returned that type itself. The one thing to note is A can be, because it's a type variable, it represents any type, okay? This is where the parametric polymorphic piece comes from. Where the constrained piece comes from is from the type class that's being determined, potentially. What's happening is you are essentially saying that a particular type signature, okay, is constrained or bounded by the set of types that have an instance of this appropriate type class. And we could see this when we construct any type on the REPL, for example, okay? It is taking in a REPL, it's taking in the type variable that's being passed in, the input, recognizing that it is an instance of this numeric type class, and then it's returning it. Okay, it's returning the value. It just informs that. You could see this also when you are talking about just any sort of function that's available. So like, for example, let's go ahead and let's do info info is -0. So in this case here, we could see that is -0 is going to take in any value, and it returns a string. Sorry, it returns a Boolean, whether or not it's not. But it's constrained because of the type class that's being on its real fractional or a floating number itself. So these are the particular constraints on the input that's being passed in. Okay, so if we pass in, say 5.7, you'll see that it's false. If we pass in -0, it's associated with hello. You'll see immediately that you'll get an error. Okay, because it is not a number. It cannot construct itself on these type constraints. Okay, this is where the constraint piece comes into play. Let's look at a few more type signatures, specifically with specific to numeric types itself. Okay, so going back to what we were talking about in numeric types. Okay, because we just looked at constraints and polymorphic types. So what this shows us is that what this value is being passed in is it's being constructed as a constrained polymorphic value with the type numeric, with the type numeric type class instance of A, and then it returns the value itself. Okay, this information is type information that the underlying THC compiler uses, but it's important for you to know how to grab this information, how to actually read this information, because this is used a lot when you're dealing with type signatures. Okay, you can also deal with this by looking up specifically not. You could do any of the type signatures of functions. Not as an example. As you can see here, not is actually returning. It's taking in a bool and returning a bool. This is actually going to introduce us to the next thing that we're going to be discussing, which is the type signature of functions themselves. But I'm just illustrating. Sorry, wrong. Plus T. That's what I need to do. So now it's not going to do anything. Okay. Yeah. All right. So let's look at a function again. Okay. Not is defined as a function that takes in a Boolean and returns a Boolean. Okay. The arrow here is slightly different than what we saw with when we actually queried a type like 5. Okay, like a type class. Okay. These are slightly different arrows, but they are important to know that they mean different things. Okay. You might think that these are the same thing, but they're not. Okay. The arrow with the single dash basically comes from mathematics. It's saying that you could think of it as a mapping operator. All right. In a lot of cases, it's taking a Boolean. So like in not, when you're reading this, it's taking bools and mapping them to the set of bools, or the type bool. So it's taking an instance of type bool and mapping it to an instance of type bool. Okay. The left-hand side of the arrow operator is the domain of the function. Okay. The right-hand side is known as the codomain, or the range of the function. This is all from mathematics. You can actually pick up the same exact knowledge for this. If we look at the actual arrow operator itself, it itself is actually a function. Like it's defined just like any other thing. It is a function that takes in 2 arguments. Okay. the first argument is input, and the second argument is going to be its output, its return value. Okay. It is technically an infix operator that is right associative, and it takes the highest precedence. Okay. This is very important to be aware of, just because, well, there's a couple things to be aware of about this. One is A and B are just like our pair operator that we saw earlier. Okay, they are two type variables of potentially distinct types. Okay, so A may not necessarily be equal to B. The other thing is since it's -1, remember operator precedence. This means that technically speaking, this is the highest precedent operator here that you're going to be dealing with. Another thing to be aware of is the tuple constructor. We can, well, there's a similarity now. One is the tuple constructor kind of expected that you need to apply to at least two values to construct a new tuple. But the thing is that also that's only for constructing new tuple values. Okay, you can partially apply those and actually create tuple factories associated with the partially applied functions that contain, the arguments bound to a particular value. In a similar fashion, although this is an infix operator that takes in two values, A and B, the input value and the result value. The input type and the result type. You got to be very careful there about the terminologies. You can technically partially apply you can also partially apply a function, okay, and create a new function. Again, we've talked about this through the process of currying, and we'll touch a little bit more on this and dive a little bit more into currying in just a minute. The one thing to note though is that you could also do the same thing here. You can actually use partial function application in currying to actually go and create these function factories where you have something partially applied and you actually return, go ahead and, create a new instance of this function factory that essentially creates instances of functions where the first argument is partially applied. Okay. There is one difference between the tuple constructor and the function itself in terms of their signatures. Okay, and that is the way I have to show this is actually, let me see if I could pull up the specific arguments here. Okay, so although they may look the same, function types do not have data constructors. Okay, whereas tuple types can have data constructors. Okay, so you might have pairs and triples and quadruples having their own data constructors, much like false and true has their own data or no argument data constructors. You could do something similar with data constructors for tuples, especially when you're dealing with partially applied tuples, where you have tuple factories, like I said, where you return a function that has one of the arguments fixed. Those can be used as data constructors to actually create new instances of tuples, so they will end up, mapping up to the higher level tuple. Functions, on the other hand, the value that shows up at the term level, like the instance of this function, this notion, and the best way to show this is an example. Let's say add. xy equals x plus y, where add is integer that returns, that takes in another integer and returns an integer. What this is doing is if we look at the signature, hold on 1 second. All right. You can see here that at the term level, and that is, again, you could think of the term level kind of like at the top level when the value is loaded into your REPL. At that level, the function that is ultimately created here, okay, the value that is ultimately created here is an instance of the actual function that we've defined, okay? Functions themselves are first class citizens, but more importantly, functions are values, all right? They are not types. The type is in the signature is the type of the function that we've defined. But at the term level, this rule that you see here, okay, is the pattern that's constructed that's ultimately going to be used by the REPL and in your code if you're using compiled versions of your code, that's ultimately going to be enforced, okay? So although this is the type signature, the ultimate thing that's bound to it is the value, which is the function itself, the Lambda expression that was created at construction time, which is this rule. I know it's a little subtlety, but and a little subtle and a little difficult to maybe understand as to why this is important. But you'll see later on that knowing that functions are values versus functions being types will become immensely important when we start using them in cases, especially higher order functions. This is where a lot of this stuff will end up kind of tying in together. Okay. Functions themselves, we know, can be applied to one or more arguments, okay? Then the way the type signature itself is written, it can be seen that we're essentially applying this to one or more arguments, okay? Since this arrow is an infix operator, it's actually telling you how the function itself is actually going to go from left to right, okay? One thing to note about the arrow operator, which I didn't bring up, but you may have been keen on, is this being right associative, okay? The function application is different than the parameterization, okay? Parameterization of the function is technically right associative, and this is really associated with how values are being passed in to each other, okay? This becomes important specifically for function composition, okay? If you have a function that takes, and I'm going to write this using this, a function that goes from A to B, okay, and a function that goes from B to C, okay, there's only one direction that this can be applied to, right? And that is you can only technically apply the composition of these two by doing f of g, not g of f, okay? So this is equal to f of g of x, okay, of some x, where x is some value of a, of type A, okay? The type signature of this guy, okay, for x in A, is going to be the following. It takes an A, okay, and it goes to C. But really what's happening is when you're composing these two functions, what it's doing is it is saying it takes an A to B, okay, and it takes a function that goes from B to, actually, hold on, I think I did this wrong. Oh, yeah. What I mean is, the only way to actually return this is actually g.f instead of f.g. Yes, this is why we're going through this example here. So this is g of f of x. And the reason why and to show how this is right associative, the return types all have to line up. So the return type of f is b. The input type of g is b. So that means the only way for this to even fall out is going to be g.f. Okay? And this is going to be an A to C, okay? The reason is it's going to take an input A to B and an input that takes a B and returns a C and returns a C. This is essentially what you should look at this as, okay? And this is how you would line this stuff up, okay? The return type is determining the associativity, but function application itself is left associative, okay? It's going to go from the innermost argument, and that's going to be the leftmost argument that's going to be applied. This is, I know, a little confusing, but if you just think about this exercise of composition and the exercise of aligning the return types, then you will know that it's going to go from the innermost function and it's going to go to and apply itself, and then it will go from right to left, okay? So the arrow itself determines only the mapping, and that's left associative, but the actual application, and the application is also left associative, but the return values determine how the values are going to be passed in, and that's right associative. Does that make sense for folks? Oh, there's a question here. Are some of these, okay, so there's a question here that we had regarding numeric types. Are some of these more general numeric types, like fractional, only used during compilation, or can a value at runtime be considered fractional? Okay, good question. So there's a question on fractional and numeric types. The answer to that question is very, it depends, okay? You can enforce a fractional type class on a signature and say that these can be constructed. But I don't know, I don't believe you can, actually, you know, I take that back. I think you can actually go ahead and use the same syntax that I used for the integer example that constrained on the integer to determine whether or not this numeric type is fractional. You can definitely consider a value at runtime to be considered fractional and enforce it by using the : operator, like I used the defined as operator. Much like how I constructed it in the REPL, you could do that too as well, not only during compilation but also during runtime. I suggest you try it out, folks who've seen this. So let's check this out here. As an example, let's see. 5 : I don't know if this is going to work because of fractional is a type class, and I think there's a specific notation associated with it, but I'm not entirely sure to actually construct it this way. Yeah, that's what I thought. It can infer the type class, but it cannot infer the subtype. You have to create a concrete, in this like notation here, you're going to have to create, you're going to have to use one of the fractional types. So like, say, I think rational is a type. So we could say this. And now if we do type x, you can see it's the type rational, but it internally is a fractional type class. I'm not entirely sure how you would actually enforce a specific type class during the runtime to restrict a specific construction. That's something I would have to look at. That's a good question. I'll look into it and I'll get back to you on that. Any other questions of what we've covered so far? I'll just hold on to a minute here. Okay. Here, any more questions? Let me go back to the. Let's look at another function type signature to continue reading type signatures here, and that is info on, say, FST. Okay. In FST, we know that it takes a pair and returns the first element of the pair. Okay. We know we can read this as basically it takes in a pair and it maps to the first element of a pair, which is its return type. Okay. The way function application essentially works exactly, and the way the arrow operator works exactly in terms of function application is that we're applying the function to something that gets bound to the first parameter, which is, if we say f is using the syntax f colon a arrow b, it's bound to a, the pair is bound to a, and then it returns whatever result type to b as a result. Okay. In this case, the first function type itself has two parameters. The function type itself, which is again the arrow operator, has two parameters. The first is the pair, and the second is the result type, which is a. And the result that we're seeing in the function signature and the type signature is the type of what the result is going to be, which is the same as the first value. Okay, so we don't know, since a and b here are type values, and a itself is going to be a type variable too as well. Okay, this is a generic function signature because we don't know what exact types are actually being passed in. It's saying that you could pass in a pair of any two types, and you're going to return the type of the first variable. Okay. Now, one question might arise when you're looking at this, because this is a type signature. Okay, this is saying that we know the value that's being returned is going to be the same type as the first, the type of the first member of the pair. Okay, we know that these two are the same type. Okay, but we don't necessarily it's going to be the same value. Type signatures, this is one limitation of type signatures. Okay, it's telling you only the type guarantee, but it doesn't tell you the actual value guarantee. Okay, technically speaking, I'm not I'm not saying that this is valid. This should be valid, but it is true based on this. Oh, another question. Is A arrow B, arrow B, arrow C to C. No. Technically, I would. That is actually not the same. Okay. So there's a question that came up on type signatures that I think is important to discuss, and that is, we have this example here, okay, which is g.f, which is taking any A that returns a B, okay, and any B that returns a C, and we're saying that we're returning a C. This is slightly different. This is different from a function, let's say h, that takes an A and a B and returns a C, okay? In this first example, we're saying that we're taking in two functions, okay, and we're returning essentially a C value, okay? The results of the first function is essentially going to be passed into the second function, okay? And the second function is ultimately going to be the one that's going to return the C itself. The example here that that we see is we're taking, this is a function, this is representing a function of two arguments, okay? That's essentially what this is, okay? This is saying that h is a function that takes two arguments, A and B, and returns a value of type C. The composition does not necessarily actually say that we're taking a B as a second argument, okay? We're composing the result type of a B taken to C, okay? And we're using the result type of F, which is B, as an input to G in order to actually get that C. So B is not necessarily a second argument. It is actually the result of applying A to the first function, okay? This is why it's still technically an argument of one, it's still technically a function of one argument. Does that make sense? Function composition is always going to be whatever the input variable is of the, the innermost function, the first function that you're going to be applying to, the innermost type that you're going to be applying to. But it's always going to be the innermost input, okay? So the first function's innermost input, and the last function application's result output to actually be the function signature of the function composition. But you're not creating a multi-argument function by doing function composition. That's a different thing. All right. I know. Let me know if there are other examples that you if you want me to go over. But this is a very important point for folks who aren't used to function composition. Function composition is not making multi-argument functions. All right, you are not making multi-argument functions through function composition. It's a different thing. You are applying the results of one function as inputs into another function. So you're creating these higher level pipelines by composing functions with each other. All right, and this is actually a basis of creating larger scale programs, because if everything is returning some sort of value, obviously you can construct anything by doing a pure composition. As long as the types line up, it'll just, run each function application one after the other. Okay. Let me go back to my in here. All right. Let's look at, so to go back to first just for a minute here, because I think it's important to illustrate this point. First, technically speaking, could have been defined almost completely incorrectly, but still matches that type signature, which shows why you need to be careful about how your types. You still need to test the implementation of your definitions. An example of this is you could technically define first. Let's say, let's do this up here. My first takes in an AB, returns an A. Okay. Actually, say my func here. Okay. What? All right. My func equals A. Okay. Okay, we could do this. All right. So one thing to be aware of, and this is something that I don't think I can actually do it in this appropriate time, is technically speaking, you could potentially violate this by creating a pattern matching that essentially makes sure that you're returning the identity always of the set upon which it's the argument that's being passed in that's being returned. But what Haskell prevents is a lot of this sort of stupidity by actually essentially allowing you to write, these sort of patterns based on the variables that are being returned here. You cannot present concrete values here. And since, again, we could verify that these types are all matching, what ends up ultimately going to be returned by that function is going to be something that validates the type signature, okay? What I want to illustrate here, and for some reason I can't seem to get this particular example correct. I have to actually go and look into one way to actually write this. It might take a little bit more finagling, if you will, to actually illustrate this example. But since this type variable actually can be of any type, as long as you know the type ahead of time, if you can actually construct, actually I could do this in a very simpler way. Instead of using generic types, let's say, for example, we have a concrete example of this, okay? Let's say that we're taking a function that takes two integers and returns an integer, all right? Two integers and returns an integer. These are all concrete types. Okay, this works. We've seen tuples can actually be defined this way. Technically speaking, this here is a valid signature. All right. We said it's taking two integers and returning an integer. We're matching the same types, but we're not using any of the arguments that are being passed in. All right. Let's call this, instead of my func, int first or something like that. We know int first should act like first, but it's not actually acting like first, okay? It's ignoring the 2 arguments and returning those, okay? Obviously, this is a contrived example, but it illustrates one particular point that I wanted to illustrate about type systems and static typing in Haskell, okay? The type signatures only guarantee the types that are being returned and the types that are being mapped into a particular function, but it does not at all prevent you from doing dumb things, okay? As long as the types match, you can actually guarantee that your types are your program is actually going to work. I know who's stupid enough to do that given the name of the function signature, but it can happen. Like if you have simple programming mistakes that when you're implementing something, it might be the case that the types that are all lined up, everything is hunky-dory from a compilation perspective. It's ensuring correctness, but because of your system requirements and the way you implemented it does not match up, you are actually still ending up introducing programmer errors that are going to have to be debugged. All right. So this is something just to be aware of. Okay, when you are writing your code, if your code does not match, not only do you want to ensure type correctness, you want to also ensure correctness of behavior when you're actually implementing some of this stuff. And if you're you're diligent enough to actually implement your types and your type signatures and your constraints correctly, the type system will end up being a tool to ensure verification of your program as you're moving on in your journey. Okay. Let's look at another thing. We've talked about first and second, but what about something that takes in a list? Okay. Let's look at length, for example. Okay. Length, as you can see, takes in any foldable. All right. This is a foldable type class. Remember, this is when you hear able, or if you see something like num or show or something, you're dealing with type classes, especially ones that because they're taking in some sort of type. And what this is saying, it's taking a foldable of t, and then it's creating an instance of that type. Okay, t of a, because this is type of any type, any subtype. Okay. T is some sort of container. It could be some sort of container, but it's anything that's foldable, and it's of any type, and it's returning some sort of integer. Okay, this is how you should read this. Okay, it could be a list, it could be a vector, it could be anything that essentially implements the foldable type class. And what's happening here is it will return you essentially a fixed precision integer. Okay. If it's bigger enough, I think there might be some sort of promotion values for this, but I'm not entirely sure. It looks like this will only go up to some sort of limit in terms of the number of foldable operations. As with anything foldable, just like list, it does not actually tell you what the size of the underlying type class is. All right. While the instance of the type class is. And additionally, we don't know the types of that's being passed in, and nor do we necessarily care because of the fact that since length is actually looking for a number of members, all right, it can be any number of members. It could take a list of integers. It could take a list of, strings, anything. And as long as they're all of the same type, you're actually okay. It will actually convert it and then give you the number of values associated with it. This illustrates one specific thing, which is the fact that the generic functions, all right, with a type class as an input, can go ahead and be used in a generic action because those operations actually exist for those instances of those underlying collections. Okay, So whether you're using list, vector, or whatever, vector I think is defined in not in Prelude, but it's implemented in another another third-party library that you can actually load in. Those will essentially implement this foldable type class, which means you could actually use all of the standard operations the same way. Okay. The type signature here is slightly different from the first type signature, mainly in that in our first one, we're not even talking about type classes at all. We don't need anything to worry about type classes, but here it's clear that we needed to use some sort of type class. This, for the newbie Haskell programmer, is often a question, and this is something that I've started asking myself as I've been going through my Haskell journey: when to use type classes, when not to use type classes. We'll dig into this in a little bit more detail in another episode, but to put it briefly, if you know you're writing sort of a generic algorithm in which the characteristics of the algorithm expects types to have certain operations, what you're effectively designing is a generic algorithm for a particular type class, which means it would be better and it would be in your best interest to essentially define that type class. Well, first, check to see if the type class doesn't already exist, and if it doesn't exist, define it. If it does exist, use that defined one to define your new operation. Okay. But if you're creating essentially a standard a generic function in which you just don't care what type's being passed in, at that point you don't necessarily need to use type classes. You could just use generic type variables and let the underlying Haskell compiler do its thing in terms of type inference to determine what best it should be appropriate to do. All right. Let's talk about very quickly here. Oh man, can't believe we're already 2 hours here. I'll be very brief about this one piece here, and then we'll cover occurring and polymorphism next week and type inferences. But let's touch base very briefly and very quickly on revisit numeric functions for just a minute here. Okay. So let's look at, for example, plus and minuses. Okay, we've already looked at this one. We've already looked at, let's say, division here. All right. Remember, when you're dealing with operators, you're actually, in order to query the types of these operators, especially the infix operators, you need to wrap them around parentheses. And by doing so, you're essentially asking for the function signature for that. And by doing so, you have the ability to now, call these guys as normal functions in prefix notation. But if we're looking at these signatures, you can see some very small subtle differences, but important differences. All right. One, addition can take any numeric type, and as long as it has 2 arguments of a numeric type, it will go ahead and return a numeric type. Okay. This is how you should read this. Okay. The type signature here, the type constraint, all right, used by the type class, is actually applied to every instance of the variable, the type variable in the function signature. All right. This is very important to know, because this means that numeric is a type constraint across all of the instances of the type variable in the function signature. Okay. All of these have to be numeric values in order for this to be a valid function evaluation. Okay. Similarly, in division, all of these have to be adherent to the fractional type class, right? So the operations associated with fractional are slightly different than numeric. If you recall, if we do info on fractional, you'll see that it has to have the division operator defined, it needs to have reciprocal defined, and it has to have some sort of operation that could convert a rational number to its type defined to as well. All right. This again applies to all values in the type class here. All right. That means all of these in this function signature, all of these type instances of the type variable a are all actually implementing. I'm using implementing in a very generic in a very specific sense. It's implementing the fractional type class, so it's defined for that particular subtype. So if you have a new type that you want to treat as a numeric type, and you want it to support division, you must define the fractional type class against it, which means you need to define the operations that I've just listed here in this class num fractional a, in order for the Haskell compiler to register it as being that type class, in order for the operation to actually occur. The reason for this is the compiler gives it infers the least specific and most general type it can, given the arguments that it provides. Given that type classes are more or less kind of like, think of them like interfaces in object-oriented programs. I'm using that very loosely for now, the term interface, but it's the closest analogy that I can come up with. It's basically saying that since a type class is kind of restricting the operations that this particular type variable needs to adhere to, this type variable essentially is further constrained by the operations that are defined by the type class. So this is not just a completely generic function. It's constrained based on the interface that is provided here, which represents the fractional type class. All right. When we dive deeper into type classes, it'll become very apparent. But as you can already see, and you're probably seeing this already in the function signatures that I'm showing you here, these operations are themselves nothing more than type signatures that have to be implemented. They're functions essentially that have to be implemented in order for this to be of this particular type. This is where the duck typing can come in from inside Haskell. This is why, although this is considered to be a polymorphic function, both plus and divide, they're all polymorphic on all the numeric types. They're constrained in the sense because they're expecting the concrete instance of this type variable a to adhere to the type class that is defined here, right? It needs to be able to, essentially, if you're thinking about it from a OO style like thinking, but again, I'd rather you try to unlearn some of that when the time isn't appropriate. But for now, you can think of it this way. It can upcast that guy to this higher level interface, this fractional interface, this fractional type class. And if it can do that, then it's obviously a subtype of that type, and it can actually then be used in the execution of this function. Okay, that's where the type constraints come from for these polymorphic functions. All right, but they are still polymorphic. All right, that's something that I want to kind of stress. Haskell has a very different way of thinking about polymorphic functions than other languages, and it stems from this ability to know what is a purely generic function, okay, regardless of the type, in which case you're dealing with a type variable, and what is a generic function that adheres to some type class, as you can see here. All right. Are there any questions? Okay. So if there aren't any questions, I'm gonna end today's session. Um, Again, we started learning about reading type signatures, functions especially. Went through kind of the constraints. We covered tuples and lists. We've covered uh, the role of types in the type system, specifically in Haskell. Um, uh, Next week, we're going to be covering function currying more, talk a little bit more deeply about polymorphisms and type inferences. We're going to cover also type assertions when we're dealing with it in it, and hopefully we'll have enough time to cover the different notions of polymorphism, both ad hoc and parametric, and even try to introduce ourselves into type classes. Um, But until next time, I appreciate all of you who joined the stream. If you enjoyed this talk, please go ahead and like it and subscribe to our Atlanta Functional Programming channel so that way you can get notifications for our weekly talks on Haskell. We also host every Saturday a Common Lisp study group that covers the Common Lisp language and its ecosystem as well. And Atlanta Functional Programming is looking for speakers. So if you're interested in giving a talk on functional programming in general, it could be in any language that you see fit. How you're applying functional design and architecture. It's something that's becoming more and more popular these days thanks to data-oriented pipelines. Please feel free to give me a shout out either on Twitter on as Unix Nerd, or you can. I'm usually on functional programming Slack has Bugram, or even on the Lisp Discord server has Bugram as well. So go ahead and ping me there, give me your talk ideas, and we can get you set up for a monthly talk. But that's